last time, given a young tableau, we defined or we showed that we saw the definition long back, but we eventually proved that V lambda, where lambda is a young tableau, is actually irreducible, and if lambda is a lambda and mu are two different young tableaus, such that their young diagrams are also different, then they are not isomorphic, and that way we got all the young tableau, all the irreducible representation of ST, the symmetric group, and and as a consequence, we also saw that if lambda and lambda prime are uh, uh, young tableau of the same young diagram, then they are going to be isomorphic. Yeah. In fact, you can. So I gave you more like a heuristic, a proof using the fact that there are only so many irreducible representations. But you can actually give an isomorphism. Yeah. So in fact, we know that if lambda and lambda prime have the same young diagram, then lambda prime. You can write it as G lambda for some G in ST. Yeah. And then I think then we know that C lambda prime. Uh, so then P lambda and Q lambda are going to be conjugates. Yeah. So P lambda is going to be, I don't know, G inverse. P lambda prime is going to be G inverse P lambda G. I hope. Yeah. Or conjugate by G or G inverse, one of the two. Yeah. And Q lambda prime is really. So I think I wrote it down last time. So I think this is right. Yeah. G inverse Q lambda G. So what we lambda prime is. So I'll just check here once. So yesterday we saw this identity, and this was in the proof of this lemma. QG alpha is G, so it's ulta of this. G QG mu is G Q mu G inverse. Yeah. So let's fix this. So QG lambda is PG lambda is, yeah. So I mean, one could verify it as well directly, but what's this? G inverse, yeah. And from here, you can check that A lambda, B lambda, and C lambda are basically conjugates by G. Yeah. So for the corresponding lambda prime. Yeah, so C lambda prime is just G C lambda G inverse. Yeah. So because that is true for A lambda and B lambda as well, A lambda prime and B lambda prime as well. And hence for C lambda prime because the product of these two. So from here you can show that though V lambda prime and V lambda are not the same sub-representation of ST, but V lambda prime is isomorphic to V lambda. In fact, the isomorphism will be either multiplication by G or G inverse. Yeah. So by G, and I'm not referring to the direction. So it's either this way G or the other way G. Yeah. So you can check that these are isomorph and the map is multiplication, and the ST equivariant map is multiplication by G. Okay. So multiplication by G is going to be a map from one to the other, and yeah. Okay, so so one could directly prove this as well, but nevertheless, let's come to the character for the formula for the character of Young diagram. So This is called Frobenius formula. So we'll see the formula. The proof is a bit involved, meaning it's computational, but yeah, so it gets a bit messy. So I don't think I'll do the proof, but at least the formula we'll see. So you can use the formula to compute the character tables and so on. Yeah. So let lambda be a Young diagram and chi lambda be the character of V lambda. So you want to compute chi lambda for every element of ST. Yeah, but we know that chi lambda is a uh, uh, is a class function. Yeah, so on all conjugacy classes is constant. So let's try to figure out what will be the value of chi lambda on a particular conjugacy class. So how do conjugacy class in ST look like? So basically, we look at the disjoint cycle decomposition. Yeah. So I'll just introduce this notation. So let Ci tilde be the conjugacy class in ST, where the disjoint cycle decomposition has I1 1 cycles, I2 2 cycles, I3 3 cycles, and so on, and ID d cycles. Yeah. So this I tilde is a D tuple. So of course it can't I mean, the sum, it has to be, total has to be D. Yeah. So I mean, if I1 is D, then the rest has to be 0. And if ID is 1, then the rest has to be 0 and so on. Yeah. So this joint cycle decomposition looks like that. So this, I mean, I tilde can't be arbitrary. It's subject to this this restriction. Yeah, summation I alpha times alpha has to be D. So we want to compute what will be the value of this character at this on this conjugacy class. So it will depend upon lambda and this D tuple I1 to ID. Okay. So so what you do is, so lambda is some lattice, yeah, some Young diagram. Okay, so something like this. Yeah, so there are certain. So what you do is take K to be at least the number of rows. So you can take K to be 5 or 6 or 7. So if you take the smallest, the formula will be simpler. Yeah, but technically you can take K to be bigger than 5 as well to apply this formula. So let K be the number of rows in this lattice lambda. And you introduce same number of variable x1 to xk. So of course, if you take K large, you are introducing more number of variables. Yeah? And let lambda x be the polynomial xi minus xj, so a product of xi minus xj, I less than j. Okay. So and p px1 to xk, pj of x1 to xk, you define it to be the sum of x1 power j x. So you x1 power j plus x2 power j up to xk power j. Yeah. So for j greater equal 1. Yeah. So I'll come to, I mean, it looks like I'm defining a lot of things, not giving you the formula, but this is the fastest one can get to the formula. Yeah. So Pjx are these polynomials. So P1x is just x1 to xk. P2x is squares, sum of squares of xi's, and so on. Okay. And Lj are some integers which we is positive integers. Yeah. So is lambda j plus k minus j. Yeah. So L1 is lambda 1 plus k minus 1. L2 is lambda 2 plus k minus 2, and so on. So as you can see, this LIs, they are decreasing. Yeah, most lambda 1 subtracted. So LIs are also decreasing numbers. Okay, and this is for j between 1 and k. Okay. So now, lambda, so lambdas are, of course, lambda, you know what it is. Yeah, the lambda is the partition. So lambdas are that length of these rows. Yeah, lambda 1 to lambda k. So of course, if you are taking k to be bigger than this, then last few lambda k's will lambdas will be 0. So now the formula. So this is the formula. So maybe I should box this formula. This is the Frobenius formula. So the value of the character on this conjugacy class Ci tilde is the coefficient so the box is incorrect. I have to make a bigger box. So is the coefficient in this polynomial. So this is the polynomial delta x. Delta x was this matrix, this polynomial times the product j equals 1 to d I pj x for ij. Ij's were the component of the Ci tilde, those ij's. So we want in this polynomial the coefficient of the monomial x1 power L1 to xk power Lk, where lies are these things. Okay. So, so of course, I mean, the formula is complicated because the action is sort of complicated. Yeah. So though, I mean, it looks like one should be able to determine, but and that is true, one can determine, but so it turns out that the formula is a bit complicated. Yeah. So this is the Frobenius formula. Okay, so does the formula make sense? And do you see what the what the formula is? Does it make sense? Are you guys still with me? Can you all hear me?
Yeah, yes, sir.
It says my sharing is paused for some reason. Can you see? Okay. Okay, so does the formula make sense? Meaning, okay, so maybe we'll work out one example, yeah, to see that one can compute these things, at least in a smaller case. So not this lambda. So and maybe d also will take small. So so actually we'll do some familiar way, yeah. So maybe S4 we had computed, yeah. So S4 we can take. So I mean, let's not take the trivial. So let's take this one, yeah. One can take this as well. So line and this I don't want to take. So maybe let's take this one, yeah. This 4. It's okay. So lambda 1 equals 2, lambda 2 equals 2, k also equal. So too many 2's here, yeah. Maybe it's not. Well, it's okay. Let's see, yeah. So I can do. Yeah. Let's do this. Yeah, it's okay. So so you want to compute the character table of. So there are what are the conjugacy classes in S4? So no, one is identity and transposition. So maybe I'll write it in this notation. Yeah. So C So identity corresponds to taking 4 1 cycles, yeah, and zeros. And then transposition, so 1 transposition, so 0, and then 1 transposition means 2 1 cycles, yeah. So 2 1 cycles, 1 transposition, 0 3 cycles, and 0 4 cycles. And what else is there? C, so 1 3 cycle. Then if there is 1 3 cycle, and the other should be a 1 cycle, and then 0 0, and 1 3 cycle. Yeah, so this is not the right thing. 1 0 1 0. This is right. Yeah, and then maybe 1 4 cycle. So C, 4 cycle means the rest has to be 0. And finally, there is one more, yeah, which is actually this this guy. So 2 2 cycles, yeah. So C 0 2 0 0. Yeah. So I think I've exhausted all the conjugacy. There are 5 conjugacy classes. Okay. So let's try to compute this in these guys. So okay. So K is 2, so so lambda x is at least easy to compute. So lambda x1 x2 is just x1 minus x2, I suppose. Yeah. So that turns out neat, nice. So if there are only 2 rows, then things are easy. Yeah. So it's just x1 minus x2, and delta, sorry, delta x1 x2 is x1 minus x2. P, so pi is, yeah. So I don't. So we'll have to compute each of them. Yeah. So let's try to compute it for this 2 1 0 0. Yeah, for the transposition. Chi. So this is our lambda. Chi lambda C 2 1. Yeah. Maybe zeros I'll ignore. Yeah. So I'll just write it this way. No, shouldn't ignore. Yeah. If 0 comes before, then it's a bit of a problem. So 0 0. So what will this be? So we have to take delta x, L1, L2, etc. I have to compute. Yeah. So so what is L1? What is L1? So L1 is lambda 1 plus k minus, L1 is lambda 1 plus k minus 1. So lambda 1 is 2, and lambda 2 is also 2, plus k is 4. So L1 is 3, and L2 is 2. Yeah. So so we want the coefficient of. So this is the notation for coefficient of x1 power L1 to x1 power Lk. So I'll use this notation. So x1 minus x2 times product of these guys. So the next, the last 2 terms are 0. Their power, 0th power is 1. So I just have to take the power of the first 2 terms. So x1 plus x2 whole square times x1 square plus x2 square. Yeah, because I1 is 2 and I2 is 1. So we get power 2 here and power 1 here. And P1 is x plus x2, and P2 is x1 square plus x2 square. And then we want the coefficient x1 power 3 and x2 square in this guy. Yeah. And what is that coefficient going to be? So I hope I haven't messed it up. The total degree is 415. Yeah. So there should be some guy at this coefficient. So so I want x1 cube. Yeah. So the only way to get x1 cube is you have to have this x1 square term. Yeah. So x1 square times x1. So it comes. No. So let me just expand this a bit. Yeah. So I don't know if there is a shortcut to this thing. x1 minus x2. x1 square plus 2x1 x2 plus x2 square times x1 square plus x2 square. Yeah. And we want the coefficient of 3 x1 cube x2 square. So yeah, so what we can do is yeah, so x1 cube x2 square. So let's just collect the terms which will have that. Yeah. So 1 and x2 square. So 1 and then so if I take x1 cube, so 1 plus 1, 2. So I'm just trying to collect terms here. Yeah. And okay, so that's it. So if I take the first x1, this is the only way we can make it. These are the two terms we'll get. So then, of course, yeah, x1 cube, and then x1 squared on this. Yeah, now minus, it's coming out to be negative or something. Yeah. So x2 is negative. Then I want minus 2. So minus 2. Yeah, so that is the only way possible. So so my x2 square, I have to take this term and then the rest is fixed. Yeah, and I can't do anything else. If I take x1 square here, then that's not. Yeah, so it turns out to be 0. Huh? So the coefficient of this is 0, which is right, is it? So does anyone remember from the character table of C4, S4? So so for transposition, it turns out that, so I took transposition, yeah? So this turns out to be 0.
Yeah, it's 0, sir, it's correct.
It's 0, okay, good. So this is, so does that make sense? So you see that you can indeed calculate it, yeah? And you can do the same thing with the 4 cycle. And so if you plug in these values, I1 to be 4 and the rest to be 0, then you will get the dimension of this representation corresponding to this guy. So what was the representation? This was the standard representation, is it?
No, this is Fulton just calls it another representation. This is the one he gets in the end after all the others.
Oh, yeah. So after, yeah, so we had some, we have 5 representation. One was trivial, alternating, standard, and then you tensor standard with alternating. And then this is the 5th one, yeah? Whose character we found out, but we didn't give a description of the representation. So I think I did we do S4? I thought we did S4.
Yeah, we did.
Yeah. But maybe I didn't tell you what was the remaining representation. So chi4 tensor chi2. What is chi4? So I'm just trying to recollect here. Chi4 is the standard representation. Yeah. And chi3, phi3 is a two-dimensional representation. The standard representation is the three-dimensional one. Yeah. So what is this phi3? It is the induced representation. Yeah. Which we get from S3. Okay. So for that, the table is so this is the So if phi4 is the standard representation, phi5 is also standard tensor with the alternating, and so phi3 is this corresponding to this 2 by 2. Yeah, and you can see that for transposition it is indeed 0. Okay. And if you compute it for C4, you will get, so maybe you can verify this table, yeah, for using this formula. Okay, so maybe good idea to write it here. Maybe I don't want to spoil my notes. So, but the point is that you can, maybe I'll write it there, yeah. So if you, yeah, this is the page. So if you want to compare it with the with various guys, this corresponds to phi3. Yeah, the first one. This is the trivial representation, phi1, and this we know is the is phi2, and phi3 is the I think is this, yeah. And so and then you tensor it with the alternating representation is switches. So hopefully it's this. Okay, so phi4 is this. Compare with previous guy. That was some lecture 20. Okay, so you can compute all this. So you can compute the line for phi3 using this formula. Okay. So I hope this tells you how to do the computation. Okay. So using this formula, in particular, you can compute the dimension. Yeah. So the dimension corresponds to when this I twiddle, the first entry of the I twiddle is D, and the rest are 0. Yeah. So dimension of V lambda is chi lambda E, which is chi lambda of this conjugate. So this conjugacy class has only one element identity. Yeah. So it's this guy, which is same as saying take the so all the pj's, all the ij's are 0 other than I1. So you get delta x times only P1 will appear here, P1 power D. Yeah, so you get this, and you want the coefficient of L1 to Lk, where li's depend upon these lambda j's. Yeah? So you can simplify this. So by taking delta x to be, so note that delta x is the determinant of this matrix because it's this product. Yeah. So this comes from van der Waals matrix. So it's determinant of this matrix. So it doesn't. So yeah, so usually people write x1 here, but he wants it in a particular form. So it doesn't matter which order you write, yeah. Yeah, so it does matter. You want this, otherwise the sign will change by -1, yeah. So it does matter, but this will turn out to be okay. And then this product, you can use the multinomial formula to get this. Yeah. And if you, so you take the product of these two and you are looking for the coefficient of this. So if you do the simplification, after simplification, it will turn out that the dimension of V lambda is this guy. Okay. So d factorial over L1 factorial to Lk factorial, where Li is, remember, is lambda I plus k minus I. Yeah, and you have to multiply by this this factor, Li minus L. Okay, so this is the dimension of V lambdas. Yeah, so this is the formula for dimension of V lambda. But it looks a bit complicated. Yeah. So maybe let's try to compute it for this example, which we were working out. So so this is lambda 1, this is lambda 2. So in particular, we would have computed C4000. Yeah. So so lambda 1, lambda 2 both are 2. So this is 4 fact. So dimension V lambda is 4 factorial. Is 4 factorial over, so what, yeah, I have to compute L1 and L2 as well. Yeah, so L1 and L2 we had computed. What was L1 and L3 and 2? Yeah, so that doesn't depend upon I to L. So it's just 3 and 2. So L1 and yeah, so L1 is 3, L2 is 2. Okay, and so you have to put 3 factorial here, and you have to put 2 factorial here, and of course you have to put the product of these things, but here there are only 2 terms, so it's 3 minus 2, yeah, which is 1. So this, okay, so this is not guaranteed to be an integer, so something went wrong.
No, this is 2.
This is 2. Oh, okay. Yeah. Yeah, but I mean, yeah. So in the yeah, so this is 2. Yeah, so 3 factors. So it's 4 over 2 factorial, which is 2. Yeah. So this is what we. So we know that this is 2-dimensional. Yeah, from the character table, we know that this is indeed 2-dimensional. Okay, so I guess everything is fine. So this formula is okay. Yeah. So you can use this formula. So there is another formula to compute the dimension. So this looks like a complicated formula, right? But there is something called hook length formula, which will look simpler, and it's actually, but you can deduce it from this. Yeah. So somehow it looks complicated because of the way things are defined. Li's are written in terms of lambda I plus k minus I and so on. Yeah. So if you know, so maybe we will deduce this from deduce the hook length formula from this formula. But so let me tell you how to compute the dimension. So what you do is you take any. So suppose this is lambda, yeah, and you take any box. So maybe this box, yeah. So so if you take this box, it gives you a hook here, yeah. So you find the length of this hook, and that is and you put it in this box, yeah. So maybe. The length of this hook is 3 plus 1, 4. Yeah. So the number of things which go.
It will be 5, sir. You count the box itself as well.
Box as well. Okay. Yeah. So 5. You have to count the box as well. Yeah. Yeah, I think this is okay. So you count the box as well. So this is 3, this is 1 plus this 5. Yeah, so similarly you count all hook length for all of them. So I don't know, 3, 4, 5, 6, yeah. 6 plus 3, 9. So and this will be, I guess, 8, yeah, because 5 plus 3, 8. And then this became, and this 7 minus 2 is 5, so this is okay. This is 4, this is 2, this is 1, this is what? This is also 1, this is 2. So whatever, so you know what I'm doing, yeah? So 3 plus 2, 5, this is 2, this is 1, this is 2, this is, what is it?
3.
3, and this is
6.
6. 4 to 6, yeah. Okay, so this is the numbers. So these are the hook lengths, yeah. So each box entry is the hook length. Wait a second. So it's not working. Oh. Okay. Box entry is the hook length. So now the formula is in dimension of V lambda is d factorial over the product of these hook lengths. Yeah. So what is d factorial here? So I'm not going to do the computation, but 6 plus 4, 10 plus 14. So 14 factorial divided by the product of these numbers. And not factor, just the numbers. Yeah. 9, 8, 5, 4, 2. Once you can forget 6, 5, 2, 3, 2, 2. Yeah, and 3 ones. So this is so this at least seems a little easy to compute, but it follows from here. Yeah, the reason it follows is yeah. So let's try to see. Yeah. So. Yeah. So so in this case, what is Li? So maybe K is 4, yeah. And what is L1? L1 is lambda 1 plus K minus minus 1, yeah. So lambda 1 is 336 plus K is 4 minus 6, 4, 10 minus 1 is 9. Yeah. So you see L1 is this entry. Okay. L2 is lambda 2 plus K minus 2. Yeah. So L2 you can check is going to be this entry. Yeah. Is the length of this this row plus number of K minus 1 minus 1, yeah. So K minus 2, yeah. And so this will turn out to be 6, and this 3 is L3 is going to be 3, and L2 is going to be 2, because sorry, L4 is going to be 2, because lambda 4 is 2, and this K minus you'll get K minus K, which is 0. Okay, so so LIs are come up here. Yeah, so so if you in the hook length formula, so note that in this in the tableau or in the Young diagram, LIs are so in the Young diagram, LIs are the entry of the first column if the Young diagram is filled, if the Young diagram is filled with hook length. Is filled with hook lengths. Okay, so and then yeah, so then I'll have to argue. So yeah, so then maybe some induction. Yeah, so so if I remove this, then the new guy will have, this is the hook length of, so it doesn't depend, it only depends on things on the right and down. Yeah, so if I remove the first column, you'll get a new guy whose hook length, yeah, so induct on. So we want to prove these two formulas are same. Yeah, so we want to prove that these two formulas are same. Okay, so so to say that these two formulas are same, we can induct on the number of columns of lambda. Okay, so so if yeah, so if I replace so if I consider, if I replace lambda by you know something which has fewer, so I drop this. Yeah, so you go from yeah, it's again frozen. So you go from so you so given this, you assume that the formula holds for you assume that the formula holds for this guy. Yeah. So you assume that the formula holds for this guy, and then prove that the and then use the fact that the first column has the hook lengths. Yeah. So for the new LIs. Okay. So so induct on the number of columns of lambda to obtain the formula. So I'm not doing it completely, but obtain the identity. And if it has only one column, then of course it will be easy. Yeah, it's going to be one-dimensional, as we know, and both the formula should give that. Yeah. So so if it is a straight line, then of course the entries are going to be d minus 1 and so on up to 1. So so both in the hook length formula as well, and then k also is d, and you'll get this something. Yeah. So these LIs are going to be d minus 1 and so on, and this will, yeah. So maybe just do this case. Yeah. 1, 2, 3. Sorry, I shouldn't write these numbers. So let's just do this. And this is the vertical line. So from the hook length formula, it's clear that the dimension is 1. Let's just verify it for this guy. So what are the, so LIs are L1 is D, L2 is D minus 1, and so on. LK is D is 1. Yeah, and so the dimension of this guy is dimension of V. This guy is D factorial over L1 factorial. Yeah, so it's a complicated formula, looks like, yeah. But d factorial, d minus 1 factorial up to 1 factorial, and times the product of these numbers. So product of so d so L1 minus L2, L1 minus L3, and so on. Yeah, so you'll get yeah. So if you fixed L1, then you'll get d minus 1 factorial. So maybe I'll write it this way: d minus 1 factorial. If you fix L1, then L2. If you fix L2 and take the product L2 minus L3, L2 minus L4, and so on, you'll get d minus 2 factorial. Okay, so it does seem to cancel. Yeah, d minus 2 factorial, and so on. 2, 1 factorial doesn't matter. So this is again 1. Okay, so for this tower, we verified if it has only one column, we have verified it, and then you'd use this induction to go from one to the other. Okay, so this part maybe you just have to check, okay, that it will work out. So this is the hook length formula, and this can help you compute the dimensions of VLAN. Okay, so yeah, so I guess so as I said, I don't want to prove this Frobenius formula. There is in this book he has sketched out a proof. He hasn't given all the details, but you can see that it is sort of elementary in the sense that the calculations are elementary, but it's tedious. Yeah. So one of you can maybe read, and after the semester is over, one of you can present it. Yeah? So for the rest of us to see. So maybe I'll stop recording. So what was I trying to do? Stop recording. Yeah, why is it saying? Somehow I think I started recording in the cloud today.